Okay, take a deep breath for a second. Right now, as you inhale, there's actually a microscopic tug of war taking place inside your bloodstream. Down in your lungs, oxygen molecules are constantly binding to and releasing from a protein called hemoglobin. And it's not a one-way street, right? It's this incredibly delicate, continuous balance. But if you're exposed to carbon monoxide, a competing balance comes into play. Carbon monoxide also binds to hemoglobin, and it does so with terrifying efficiency. It literally disrupts the oxygen transport your muscles desperately need to survive. So this whole life and death scenario, it is dictated entirely by competing equilibria. It just goes to show that chemical equilibrium isn't just some abstract textbook theory. It's a high-stakes, real-world concept happening inside of you right at this very moment.
So welcome to this explainer. Today, we're diving into a central mystery of chemistry. It's this fascinating idea that processes which appear totally perfectly still to our naked eye are actually engaged in a furious, perfectly balanced molecular dance. Let's look past the illusion of stillness together. Okay, let's dive into this roadmap so we know where we're headed. First, we'll cover the illusion of stillness, then physical equilibrium in action, followed by dynamic chemical equilibrium, the law of equilibrium, and finally, gases and partial pressures. Let's jump in. All right, section 1, the illusion of stillness. You know, there's a really stark contrast between what we see on the outside and what's actually happening on the inside. When you look at a glass of water sitting on a table in a closed room, or maybe a sealed flask of reacting chemicals that has finally stopped bubbling, your macroscopic view tells you that nothing is happening. The mass, the temperature, the visible colors, they all remain perfectly constant. The whole system seems completely static. But if you were to zoom into the microscopic view, you absolutely wouldn't see a calm, quiet scene. You'd see intense, dynamic, nonstop activity. Millions of molecules are reacting, breaking apart, evaporating, condensing every single second. The secret here is simply that the rate of the forward process has perfectly matched the rate of the reverse process. Let's do a quick thought experiment. Picture two giant glass cylinders. Cylinder 1 is completely full of colored water, and cylinder 2 is empty. Now, imagine a continuous transfer mechanism pumping water from cylinder 1 to cylinder 2. At first, you'd see the water level in cylinder 1 drop while cylinder 2 rises. Makes sense, right? But eventually, a reverse mechanism kicks in, pumping water from 2 back to 1. Once those opposing transfer rates perfectly equalize, the water levels in both cylinders just freeze in place. Anyone walking into the room at that point would see unchanging water levels and assume nothing at all is happening. But beneath that surface, the continuous exchange is working furiously. The system hasn't stopped, it's just equalized its opposing rates into a dynamic state.
Moving on to section 2, physical equilibrium in action.
We actually see physical equilibria play out every single day. Take a perfectly insulated thermos containing ice and water at exactly 273 Kelvin. The physical amount of ice and water doesn't change, but molecules from the liquid water are constantly colliding with and freezing onto the ice, while ice molecules are escaping right back into the liquid. It's a continuous exchange. The exact same thing goes for dissolving sugar to make a thick syrup. In a saturated solution, solid sugar crystallizes out at the exact same rate that it dissolves into the liquid. And consider gases in liquids, which is governed by Henry's law. Think about that fizzing soda bottle you left open. Before you opened it, there was an equilibrium between the invisible carbon dioxide gas in the headspace and the carbon dioxide dissolved in the liquid. When you crack open the bottle, you release the pressure, the equilibrium breaks, and the dissolved gas fizzes out rapidly as it frantically tries to establish a new balance with the atmosphere.
Which brings us to section 3, dynamic chemical equilibrium. Now we are shifting from physical changes to chemical reactions, where things get a bit more abstract, but honestly, just as fascinating. Now, what's really interesting about this slide is how perfectly it visualizes the concept. Imagine a reaction where reactants A and B turn into products C and D. At time 0, you only have A and B. That's the curve starting high up on the y-axis. Because there's so much A and B, the forward reaction is incredibly fast. But as they get used up to form C and D, the forward reaction slows down. Meanwhile, as the pile of C and D grows, the reverse reaction, turning products back into reactants, starts speeding up. The real magic happens right where those two curves plateau and become completely parallel flat lines. That exact moment, that's equilibrium. The concentrations have locked into place not because the reaction stopped, but because the forward and backward speeds are perfectly tied.
And here's the super fascinating aspect. Equilibrium literally doesn't care where you started. It's an inevitable destination. Look at the synthesis of hydrogen iodide. If you seal pure hydrogen and pure iodine in a flask, they're going to react until they hit a specific balanced mixture with hydrogen iodide. But if you take a completely different flask and start with only pure hydrogen iodide, it will break apart in the reverse direction until it reaches the exact same balanced mixture. As long as the temperature and the total number of atoms are the same, the system will always find its way to that identical, inevitable equilibrium state. So for decades, scientists knew these concentrations leveled out. But how could they prove the molecules were actually still reacting? Enter Fritz Haber and a truly brilliant isotope experiment. Haber synthesized ammonia from nitrogen and hydrogen. Once the reaction hit that seemingly static equilibrium, he played a little trick. He introduced deuterium. Deuterium is basically just a heavier, traceable version of hydrogen. Now, if the reaction had truly stopped, that heavy deuterium would just float around doing nothing. But when they checked the mixture with a mass spectrometer later on, they found massive scrambling. Molecules like ND3 and NH2D had actually formed. The heavy isotopes had completely mixed into the ammonia. This was the absolute smoking gun, undeniable proof that the forward and reverse reactions were still firing back and forth, furiously swapping atoms even when everything looked perfectly still.
All right, Section 4, the law of equilibrium.
Since we've firmly proved this molecular dance exists, we really need to look at how to calculate it. Back in 1864, two Norwegian chemists named Goldberg and Waj figured out exactly how to quantify all this chaos. They proposed the law of chemical equilibrium. It basically states that at a specific temperature, if you take the ratio of your product concentrations over your reactant concentrations and raise each to the power of their stoichiometric coefficients, the balancing numbers from the chemical equation, you will always get a constant value. This was absolutely crucial. It was the vital translation from a microscopic concept to a mathematical certainty. So the crucial point is right here in this formula. Notice how products C and D sit on top and reactants A and B are on the bottom. The capital K with the little subscript C stands for concentration. Those square brackets specifically denote molar concentrations at equilibrium. And those lowercase superscript letters, they're simply the numbers you use to balance the chemical equation. It really doesn't matter what your starting concentrations are. If you run a million different experiments at the exact same temperature, when you plug the final equilibrium numbers into this specific fraction, it will always simplify down to the exact same constant, Kc. Now, because the math is so strictly tied to the equation, there are a couple of golden rules you absolutely can't cheat on. First, if you decide to write the reaction in reverse, swapping the products and reactants, your new equilibrium constant is just the inverse of the original, basically 1 divided by Kc. And if you multiply your entire chemical equation by a factor, let's call it n, to clear fractions, your new constant is simply the original Kc raised to the power of n. This means whenever you quote an equilibrium constant, you have to explicitly state the exact balanced equation you're referring to. Otherwise, the number is literally meaningless. Finally, Section 5, gases and partial pressures. Up to this point, we've focused on molar concentrations, moles per liter. But what if your entire reaction is taking place in the gas phase? When dealing with gases, especially in an industrial setting, it's often way easier to measure pressure than concentration. Thanks to the ideal gas law, we know that at a constant temperature, the partial pressure of a gas is directly proportional to its concentration. So chemists use a different constant, Kp, where P simply stands for pressure. We use the partial pressures of the gases in bars instead of bracketed concentrations. What's super fascinating here is how interconnected this all is. You can easily translate between pressure and concentration using this simple bridge equation. Kp equals Kc times RT raised to the power of delta N. R is the standard gas constant, T is the temperature in Kelvin, and that delta N is just the number of moles of gaseous products minus the number of moles of gaseous reactants. As we wrap up this explainer, I want to leave you with a bit of a challenge. Take a moment to just look around the room you're sitting in right now. Maybe you have a closed water bottle on your desk, or perhaps you're thinking about the oxygen circulating in your very own bloodstream. Armed with your new microscopic vision, I want you to ask yourself, what seemingly still objects around you are actually trapped in a furious, invisible, and frankly beautiful state of dynamic equilibrium? The world is vastly more active than our eyes let on. Keep observing, and thanks for exploring with me.